If your free body diagram is wrong, your entire solution will be wrong. Let's make sure that never happens. A free body diagram, or FBD, is a simplified representation of an object showing all the external forces acting on it. FBDs are essential tools in statics for applying equilibrium equations. Mastering FBDs is critical for solving all statics problems. This video is a follow-up to Forces and Vectors Explained, Statics 1.1, so ensure viewers understand basic force course concepts before proceeding. To create a free body diagram, first isolate the object from its surroundings. Consider only the object of interest, ignoring everything else that might be connected to it. Represent the isolated object as a point or simple geometric shape, such as a square for a box. This simplifies the analysis while keeping the essential information. In the free body diagram, show only external forces acting on the object. Internal forces within the object are not included. Clearly label all forces with their magnitude, if known, and direction. Use arrows to show the direction and magnitude proportionally. Clear labeling is crucial for accurate analysis and communication. The first common force is weight. Weight is the gravitational force acting on an object, pulling it downward toward the center of the Earth. It is calculated using the formula W equals mg, where m is the mass and g is the acceleration due to gravity. The normal force is the force exerted by a surface on an object in contact with it. It acts perpendicular to the surface, preventing the object from passing through. The normal force is what keeps objects from sinking into surfaces. Tension is the force transmitted through a rope, string, or cable when it is pulled tight. It acts along the length of the cable, pulling equally in both directions when the system is in equilibrium. Friction is the force that opposes motion or the tendency for motion between two surfaces in contact. It acts parallel to the surface and in the direction opposite to the motion or potential motion. When drawing free body diagrams, we often assume the direction of friction based on the context, such as opposing the applied force. Drawing free body diagrams requires following a systematic process to ensure accuracy and clarity. Let's go through each step. Step 1. Identify the object of interest, also called the free body. This is the object you're analyzing, isolated from everything else. Step 2. Isolate the object from all surroundings. Imagine cutting away the surface and any connected objects, leaving only the free body. Step 3. Choose a convenient coordinate system with x and y axes. Often align them with significant forces or surfaces for easier analysis. Step 4. Draw all external forces acting on the object as vectors. Only include forces from outside the free body itself. Step 5. Label forces clearly and consistently using standard notation like W for weight, N for normal force, and T for tension. Step 6. Indicate angles where needed, usually measured with respect to the chosen coordinate axes. Remember, consistency and clarity are essential when drawing free body diagrams. Clear labeling and proper vector representation help avoid common mistakes. Common mistakes in free body diagrams can lead to incorrect analysis. The first error is including forces that do not act on the object itself, such as forces exerted by the object on something else. Another common mistake is forgetting reaction forces, like normal forces or tension forces that act on the object. These must always be included when they exist. Forces must be drawn in their correct directions. For example, weight always acts vertically downward, never horizontally or at an angle unless specified. Proper labeling is essential. Each force should be clearly labeled with consistent notation, such as N for normal force and T for tension. Each object requires its own separate free body diagram. Never mix forces from multiple objects in a single diagram, as this confuses the analysis. Remember that incorrectly placed or omitted forces can invalidate the entire free body diagram and lead to wrong conclusions in your analysis. Consider a block resting on a horizontal surface. The forces acting on it include the weight, which pulls downward due to gravity, and the normal force, which pushes upward from the surface. If we apply a horizontal force to the block, friction opposes the motion, acting in the opposite direction. Now consider a mass suspended by a cable. The weight pulls downward, while tension in the cable pulls upward, acting directly along the cable to oppose the weight. In static equilibrium, the sum of all forces equals zero. For the block on the surface, the normal force equals the weight. For the hanging mass, the tension equals the weight. Consider a block resting on an inclined plane. The forces acting on the block include its weight, which acts vertically downward. The normal force acts perpendicular to the surface, pushing the block away from the incline. If there's friction, it acts parallel to the surface, opposing motion. The weight force can be resolved into components parallel and perpendicular to the incline. This simplifies analysis by aligning one axis with the surface. The parallel component equals weight times sine of theta, and the perpendicular component equals weight times cosine of theta. Aligning the coordinate system this way makes calculations easier, as forces now directly relate to the chosen axes. Once the free body diagram is complete, it is used to apply the equilibrium equations. The sum of forces in the x direction equals 0, and the sum of forces in the y direction equals 0. These equations are applied to the forces shown in the FBD. A correct free body diagram is the foundation for solving any statics problem. Free body diagrams have applications in structural analysis, including beams and trusses, as well as mechanical systems and load calculations in design. Free body diagrams are one of the most important tools in statics, providing the visual foundation for understanding and solving force systems. Next, we'll explore equilibrium and solving force systems. Remember to practice drawing free body diagrams on many problems to master this essential skill.